In this demonstration, I'll show you how to quickly model the blade flutter experienced by a compressor rotor using harmonic analysis in ANSYS CFX. I'll start the demonstration by overviewing the case. Then, I'll show you how to convert a blade flutter simulation that uses the time integration solution method to one that uses the harmonic balance solution method. Finally, I'll overview the results generated by the harmonic analysis. In this case, I'll use a compressor which contains 36 rotor blades. It will be rotating at 1800 radians per second. The inlet boundary condition is modeled as total pressure and total temperature in the stationary frame. Flow direction is specified by cylindrical components. The outlet boundary is described by an average static pressure of 138 kilopascals, which varies radially. The blade's vibrational motion is described by frequency and displacement mode shapes, which were prepared using ANSYS Mechanical. At this point, I have collected the steady-state results and prepared the case for a blade flutter simulation that uses the Fourier transformation pitch change method. The Fourier transformation method requires that I model two blade passages with certain interfaces set up. The phase-corrected interface uses the R1 to R1 periodic. The sampling interface is the interface between the two passages. The blade boundary is described by the blade wall boundary. I'll start converting the case by changing the transient method from time integration to harmonic balance. This is a frequency-based solution method in which transient flow variation is represented by a Fourier series for a specific fundamental frequency. The number of modes option controls the number of harmonics included in this Fourier series. In general, one mode is sufficient for describing simple flows, while more complex flows, such as those containing sharp discontinuities, require a larger number of modes. For this analysis, I'll use 3 modes. Notice that the time period, time step, and time duration options have disappeared. These are replaced by a timescale control, which may be accessed from the solver control branch. The solver will use the physical timescale control. The timescale value must be a fraction of the smallest time period involved. In this case, the blade's vibration frequency has the smallest time period, and 1/15 of that value will be used for the physical timescale. In general, a solution can be made more stable by using a smaller timescale value. To ensure that the solution reaches an appropriate level of convergence, I'll increase the maximum number of iterations to 200. The case is now ready for submission to the solver. After 200 iterations, the solver run has completed. This monitor shows that the solution has converged to a steady, periodic state. Now I can take a look at other variables, such as the aerodynamic damping. This variable has converged to a relatively steady, positive value, which indicates that the vibrational frequency is damped by the flow. Using ANSYS CFD Post, I prepared this animation showing the wall work density contour on the rotor blade. Using this data, areas for redesign can be identified to improve aerodynamic performance. As we can see, the harmonic balance transient method successfully describes the rotor's blade flutter at a fraction of the computational cost required for the time integration method. This concludes this demonstration showing you how to use harmonic analysis to describe the blade flutter of a compression rotor.